Now we have reached a stage where we can talk about how plane waves interact with different interfaces. Suppose a wave is incident normally onto an interface, what happens at the interface? That's the first question that we are going to answer today. So we talk about plane wave and normal incidence. So let us consider two regions. Region 1, which is with constitutive parameters epsilon 1, mu 1 and sigma 1. Region 2 has the constitutive parameters epsilon 2, mu 2, sigma 2. That reddish, pinkish, whatever magenta, whatever the color you want to call it, that surface separates the two regions. If I want to give this mathematically, region 1 is the region where z is less than 0. Region 2 is the region where z is greater than 0. Now we consider a plane wave which has an electric field E equal to E naught bar e to the power of minus gamma dot r. If it is uniform plane wave, E naught will be constant vector and gamma gives the direction of the plane wave and r is position vector. If the plane wave is propagating in the z direction and impinges onto the surface z equal to 0, which we call as normal incidence, the electric field can be anywhere in the plane parallel to xy plane. For convenience, we are going to choose electric field to be x polarized. The wave is x polarized. It is linearly polarized and the electric field is x oriented. This is in general, there is no problem at all. In case the electric field is oriented in some other direction, we can always rotate the coordinate system around the z-axis and align the x-axis to line up with the orientation of the electric field. Therefore, this is quite general. We are not losing any generality in making this an assumption that the electric field is x oriented in this plane wave. Now, how do we compute the magnetic field? We know this result. It is 1 upon eta a n cap cross E naught bar e to the power of minus gamma dot r. What is a n cap? It's a unit vector in the direction of the propagation constant gamma. So, in this particular case, a n cap will be z cap. Perfect. So, hi therefore z cap cross x cap, which will be y cap. So, hi will be ay e naught by eta 1 e to the power of minus gamma 1 times z. Gamma 1 we know what is that. Eta 1 also we know what is that. It can be specified in terms of epsilon, mu and sigma of region 1. Well, we know the fields which are normally fields of the plane wave which is normally incidence on this surface which forms the interface between two regions, and the surface occupies z equal to 0 plane. Now, what do we do next? We assume that this wave is going to propagate into region 2 in some arbitrary direction which is specified by gamma 2 bar, which is ax cap gamma 2x plus ay cap gamma 2y plus az cap gamma 2z. So it's propagating in some arbitrary direction and the electric field has some arbitrary polarization ax cap ext plus ay cap eyt plus az cap EZT. Remember, this E naught or whatever is that in the bracket dot AN2 will be equal to 0. So the coefficients choose the right value such that the dot product of this quantity and this quantity will be 0. Right. Now the question that we have with us is, how do you compute EXT, EYT, EZT and gamma 2x, gamma 2y and gamma 2z? That's still the question. For that, we'll have to write some field equations. Let's do that. ET is this equation and gamma 2 bar is given by this equation. You have a physical picture of these two equations. We understand these two equations. What do we do now? We will compute the magnetic field HT. In order to compute magnetic field HT, we need AN cap, which is a unit vector in the direction of gamma 2 bar. So you get AN cap as gamma 2 bar upon magnitude of gamma 2 bar, which is gamma 2. And what is gamma 2 magnitude? Gamma 2 is square root of gamma 2 x square plus gamma 2 y square plus gamma 2 z square. Brilliant. Once we know this, we can compute Ht, that is a transmitted H field, magnetic field in region 2 as 1 upon eta 2 times an cap cross E naught bar e to the power of minus gamma 2 dot r. Now, you have to compute an cross E naught, which is done with the help of a 3 cross 3 determinant, ax cap, ay cap, az cap, and we write the components of an cap, which happens to be gamma 2x by gamma 2, gamma 2y by gamma 2, and gamma 2z by gamma 2. These are the three components appearing here. Then we write the components of E and simply find the determinant of this. And this determinant, convince yourself, is given by this equation here. If there is a mistake, please let me know, I'll fix it. But my request is, please verify. For example, ax cap EZT times gamma 2y by gamma 2 minus EYT times gamma 2z by gamma 2 and so on. Please verify it. It is indeed correct. Now we are ready to enforce the boundary condition at the interface z equal to 0. At z equal to 0, the fields have to satisfy certain boundary conditions. What are those? First one is the tangential component of electric field must be continuous. That is E1t equal to E2t. Here subscript t represents tangential component. And the tangential component of magnetic field should also be continuous. That is H1t is equal to H2t. So let's try to evaluate the first one, E1t equal to E2t. For that I need E1, I need E2 at z equal to 0. EI is AX cap E naught e to the power of minus gamma 1 z. This is the incident field in region 1. In region 2, the electric field is ET, which is given by that long equation. At z equal to 0, EI will be AX cap E naught. Ignore AX cap for the moment. Just write E naught, and e to the power of minus gamma 1 z will be equal to unity, and the x component of the second equation Et is ext e to the power of minus gamma 2 xx minus gamma 2 yy, and the third part minus gamma 2 z times z is removed because we are evaluating at z equal to 0. Perfect. This is how we enforce the continuity of the x component of electric field. Similarly, we can enforce the y component of electric field. Incident field has no y component, and the transmitted field has a y component, which is EYT e to the power of minus gamma 2 xx minus gamma 2 yy. Something interesting here? Yeah, watch the second equation there. Since this right hand side is equal to 0, EYT has to be 0. A wonderful result. Now, how about the left side of that equation? Since left hand part of the left equation, that is E naught, is a constant, whereas right side is a function of x and y, where x and y can take any value, any real value in over minus infinity to infinity. In order to satisfy this equation for all x and y, we have no choice but to choose gamma 2x should be to be 0 and gamma 2y to be 0. And the moment we choose that, we have a nice result. Ext must be equal to E naught. Wow, we got somewhere now. We'll see what happens when we enforce the continuity of H. At z equal to 0, the tangential H field is continuous. Let's go through the same exercise. Write down the magnetic field at of the incident wave, which is AY E naught by eta 1 e to the power of minus gamma 1 z, and the magnetic field of the transmitted wave, which is a little long one. I don't plan to even recite this. Okay. Now, what do? We enforce the continuity of the x component and y component at z equal to 0. Continuity of the x component gives me 0 equal to 1 upon eta 2 and that little long equation there. And continuity of y component gives me the second equation. Pause. Now, pause the video. Make sure these equations are indeed correct. This is very important. This is where the electromagnetic theory and the concept and the implementation start separating themselves out. But it's my effort to keep everything together. Therefore, I need your help. I need your support. Whenever I get this kind of a pause, I'll tell you to pause and make sure you are very happy with all these terms, sign, all the symbols, everything. Then we proceed further. Okay, we are ready to proceed now. What do we know? We know gamma 2x is 0, gamma 2y is 0, ext equal to e naught and eyt equal to 0. Look at, introduce these equations, these symbols in the first equation. Gamma 2y is 0 and eyt is 0. Therefore, 0 equal to 0, that is satisfied. So there is no inconsistency in our results. How about the second one? Take some work. Let's get back to the second equation and with these known results. Introduce gamma 2x 0 and ext equal to e naught. And what is gamma? And since gamma 2x and gamma 2y are zeros, gamma 2 will be equal to gamma 2z only. Is it convincing enough? Yes. Now, if we introduce all these known values into that equation on the left, what we have is E naught by eta 1 is equal to, I'm going to get rid of AY anyway, E naught because of EXT is E naught upon eta 2, and that minus sign and minus sign will become plus sign, and we have gamma 2z which will be equal to gamma 2 because of this result, therefore that is equal to 1, and e to the power of minus gamma 2x, gamma 2y, they are 0, therefore that gives me unity. Oh, beautiful result. What does it mean? This implies eta 1 must be equal to eta 2 or E naught should be equal to 0. This is a real nuisance for us. So somewhere we have gone wrong. All this result is telling us is we have ignored something. If you have a dielectric or two media interface and a plane wave is incident normally, we cannot satisfy the boundary conditions if we assume only transmitted wave to be present. In case we have only transmitted wave, either E naught is 0 or eta 1 should be equal to eta 2. That means there is no discontinuity at all. So something has to be done. We will do that in the next video.